Hello students, welcome back again. So in this part we would discuss about the graphical analysis of energy with respect to time t, energy with respect to displacement, and the phase and phase relationship between acceleration time, acceleration and velocity, velocity and displacement, and also the case of SHM analysis. So let's begin. Let's begin with the topic graphs of SHM. In this part, we would like to discuss the graph between total mechanical energy involved in the simple harmonic system with the position of any object. Already we discussed total energy, sum of kinetic and potential, and the potential energy is just a function of position. We already discussed, and we got total energy sum of kinetic plus potential, and we got the relation at E is equal to 1 by 2 m omega square a square, where a is the amplitude. And we know that m is constant, omega is constant, a is constant, it's definite, so total energy must be constant. So we depict the graph of the equations. We depict the graph of the equations. We can see here in the main part. Means when the kinetic energy, it is just for the U, it is just the graph of potential energy and it is just the graph of kinetic energy. So means in the next slide we will discuss how this energy changes kinetic into potential, potential into kinetic. So means when the potential energy is maximum, kinetic need to be minimum, and vice versa in this case. So total sum means this is just the value of 1 by 2 m omega square a square is equal to constant. So we already discussed this part. Now in the second part we would like to say if there is a mass connected with a spring that oscillates SHM about the mean position. So we draft the graph between energy and its position. So we got when energy is maximum, kinetic minimum, and vice versa. And finally we draft the graph between E and X. We can say U is equal to 1 by 2 omega square a square sin square omega t, and for the kinetic it is just in opposite phase of potential energy and it is just a function of cos square, and so we got this relationship. And total sum is just a constant function we can see. In the next part we will discuss the SHM analysis. In this part, if we consider a spring connected with a block, now we would like to say its acceleration is in opposite phase to the displacement when it is at the straight position, because due to restoring force it would like to take system to the mean position, that is opposite in direction to the displacement. So we got at time t equal to 0, displacement is maximum but the velocity will be minimum. So what would be the acceleration? It would be in opposite phase or opposite direction to the displacement, and we got kinetic energy at that point is 0 because velocity is 0, and we got total energy, it is just potential energy we can say. Now at time t equal to t, so means we can say it is just at the max extreme position. So at t by 4 we got displacement is 0. So means it is as 0 but the velocity is equal to minus a omega. So means it is about to change the phase as it is at equilibrium or a mean position. So velocity will be velocity will be maximum, and it is about to be in opposite phase to the main equation, and we are getting total energy is just sum of kinetic plus potential. As potential is 0, so net energy is kinetic, that is a function of velocity. So we got this is the energy. Now at t equal to t by 2, so what we are getting at t equal to t by 2, so displacement is again maximum but in opposite direction. So it is positive A, negative A. So means we can say potential energy need to be maximum. That's why we got 1 by 2 Ka square. So total sum equal to kinetic plus potential. Kinetic is minimum, that is 0. Potential need to be maximum, that is sum of 1 by 2 Ka square. And acceleration is in the phase of the displacement, that is A omega square. So at 3t by 4, it come again at mean position. So what velocity will be maximum but in same direction? Kinetic energy will be maximum, that is 1 by 2 m a square omega square, and total energy is sum as equal to kinetic energy. So in the case of this time, So means these four cases are given when the system is at extreme position, at mean position, left extreme, mean position, and right extreme again. So in these five cases, we discuss the total mechanical energy, that is sum of kinetic plus potential, and acceleration at different location, different phase, velocity at different timings, and displacement equation at different locations, at extreme or at mean position. So these are the cases. So we know that velocity v is equal to omega a square minus x square. Also we know that acceleration a is equal to minus of omega square. That is always in opposite direction to the displacement. Kinetic energy is sum of kinetic energy is 1 by 2 mv square, and potential energy is 1 by 2 kx square, and total sum of energy, that is 1 by 2 m omega square into a square. That is always a constant quantity. Now in the next phase, we would like to discuss what phase is and what is a phase difference. So we know that the applet shows a number of particles in simple harmonic motion. All the particles have the same amplitude and frequency but are at different positions at any given moment. So phase expresses this difference. Each of the particles in motion can be associated with the particles on the circle. Day and night, these are the two phases. Good and bad, these are the two phases that changes with time and location. So these are called as phase. In the case of SHM equation can be drawn on a graph that is a function of displacement time t. If it is not started from 0, means either it is lagging or leading. So we define that location of angular position at any time t is just a phase. So we can say phase is just the angular position of the particles on the circle. So here we can say the case of a spring and block system, it executes simple harmonic motion. So particle just go to and fro, in which its amplitude changes from maximum to minimum, minimum to maximum. The direction changes continuously. Also we can say omega t is just the angular displacement from the mean position, that is a function of angular velocity at any time t, and it is getting displacement. So at the point y, means at the vertical dimension, in the vertical phase, we are getting in the vertical direction. When the displacement a is given, it is actually the maximum displacement. So these are positive a and negative a in this. Now next way, what do we mean by phase difference? So phase difference we can see in the graph, as we have three particles executing simple harmonic motion and we draft their equations. Y equal to a sin omega t, y equal to a sin omega t plus phi, y equal to a sin omega t minus phi, like that. So what? Phi, positive phi, minus phi or 0. So these are the phase defined for that. Now we can say phase increases continuously with time, going up to 2 pi radians for every oscillation, because we know that for one complete revolution we have a time period t, frequency would be 2 pi angular frequency. Since all the particles source in the applet have the same frequency, of course the phase increases at the same rate for all them, and so the phase difference between them does not change with time t. Only the case of lagging and leading can be discussed over here. Now phase is a one variable which can be related to all other variables easily: position, velocity and acceleration. Like if I started my journey from Delhi to Bombay at 12 o'clock in the night, my friend started his journey from Delhi to Bombay at 2 a.m. in the morning. Another friend started journey at 11 a.m. yesterday from Delhi to Bombay. So what? Although we have the distance that need to be covered is same, we have same velocity, time required will be same, but we are lagging in phase. The person who started his journey yesterday was leading. I am on time at 12 p.m. and the person, though the friend started his journey at 2 a.m. in the morning, is leading. In this way we are comparing. So these are the positions, these are the phase. But in case of simple harmonic equation, each and every equation is depicted by a graph, by an angular situation, that is just angular displacement, angular position of those particles at that particular time. Now, In mathematically, we can discuss how can we find out a relation. If we are given two equations, x is equal to a1 sine omega t plus phi 1, x2 is equal to a2 sine omega t plus phi 2, and we want to know the phase difference del phi, that is phi 2 minus phi 1. On substituting the corresponding values, omega t plus phi minus omega 1 minus t, so we are getting finally that is omega 2 minus omega 1 into t1 plus omega 2 minus omega 1. So it is a case of, means when its phase is 0 and its phase is equal to sine inverse positive a. So we can say these are the two graphs. So it is just case of this, either this one. So it is case of leading. We already discussed this part in the previous slide. Now in the second part, we are knowing the phase difference is given by del phi is equal to, so means we must know phase difference is actually equal to k into delta x. So k is just the wave propagation constant that is given by 2 pi by lambda, and del x is a path difference. So we can say del phi is equal to k delta x. So we are knowing that we are interested to calculate phase difference of two phase, that is omega t plus pi by 2 minus omega 2, and finally we are getting del phi is equal to omega by 2 radian. And actually it is just in leading phase. If omega phi is greater than 0, hence phi x2 leads then x1 by phase difference of 1 by 2. Although they have same frequency and same velocity, but they are different in their phases. Now in part 2, it is a case of lagging. Similarly, we will do the same concept. We will calculate phase of one equation and phase of another equation, and we will get equation of the phase as del phi equal to minus pi by 2. So it is just a lagging case. What we are getting from this means, although we are getting a negative sign, so del phi must be greater than 0, hence x2 lag behind x1 by a phase difference of 90 degrees. So we can say the student or the friend, so the friend started his journey yesterday at 11 p.m. at the night, at the late evening. So he was lagging by 2 hour or 1 hour than me. But the friend who started his journey 2 a.m. in the morning, next day, he's leading by me by 2 hours. So what we are getting in this phase means lagging and leading concept. That is a function of time t. So in the case third, if we are given x2 is equal to a2 minus a into sine omega t. So what is that? That is just a black equation. And x1 is a red equation. They are out of phase. They are out of phase. If we are interested to calculate their phase difference, we have to do that phi 2 minus phi 1. We can see here phi 2 minus phi 1. So that is omega t plus pi minus omega t, that is equal to phi radian. So we are getting del phi is equal to plus. And they, because what we are getting, one is already in phase, that is for this, and it is out of phase, so that is for that. So means we are getting phase difference del phi is equal to pi radian. In the part D, we are getting both of these waves are in same phase. That's why they would have same phase difference, del phi is equal to 0. So means we are getting x2 is in phase with x1 and constant with time. So means as it is not changing with that. So means they are in same phase. That's why neither leading, neither not lagging. So we are getting. Now we would like to discuss equation on this concept. We are given a graph between displacement and time t. So different condition means amplitude A is given, can be taken as 0.2 meter. Time of one complete revolution is 4. Capital T is equal to 4 seconds. Now we would like to know from the graph shown above the displacement of an oscillating location. So mass is given as 1.30 kilogram. Varying with time, the energy of the oscillating object consists the kinetic and potential energies. So what we have to do? We have to calculate the angular frequency of the oscillation. Easily we know that angular frequency omega can be taken as 2 pi into frequency f, or it can be equal to 2 pi by t. So what we are getting, that is 2 pi, capital T is 4 seconds, so we are getting pi by 2 radian per second. Actually it is the radian angular frequency of the system. So we got the answer of this question is pi by 4. Now sum of the two energies. So sum of the two energies always constant, that is equal to 1 by 2 m omega square a square. So on substituting the corresponding values, that is 1 by 2, mass is given as 1.30, omega is already calculated, pi by 2 whole square, and amplitude is given, that is 0.2 whole square. So when we will solve this relation, we are getting 1 by 2 into 1.3 into pi square by 4 into 0.2 whole square. So on solving this one, we will get some mathematical values around this, that is 3.14, that is 1.57 whole square multiplied by 1.3 multiplied by 0.01, 0.02. So we will solve this equation and we will get a constant equation, mathematical term. So means we are getting total energy must be equal to 1 by 2 m square into m into a omega square into a square, and the first part we want to know about angular frequency. So we got the answer of this part, and we did the question by substituting corresponding values in the corresponding formulas, and we got the answer. In this part, we discussed about graphs involved in energy and time, energy and displacement, along with phasor and phasor relationship between acceleration, velocity and displacement. I hope you understood the topic. So in the next part, we will discuss about terminology used in the simple harmonic motion along with the systems of SHM. And the first case, we will discuss about simple pendulum, how we will calculate time period of a simple pendulum. So stay tuned with us.